Hey guys, so today we're going to finish up kinetics, and this will be the last chapter before we take test 1, so just keep that in mind. Today we're going to talk about the things that affect rate and how we make sure reactions happen, and we're also going to talk about mechanisms. So the first thing that affects rate is temperature. Okay, you will not need this equation, but you will need to know that activation energy, which is EA, is the energy needed to start a reaction. Okay, so all reactions are going to have that point, and that's what it's called. It's called activation energy. Okay. So here we've got our activation energy. It's always from here. Okay. It's always from the bottom of the initial to the top of the hump. Okay, so it's got these reactants, H and O, they have to overcome this energy to keep going. Oh, what is happening? Okay. So just some things to keep in mind. Increasing temperature will increase that average kinetic energy. We did talk about that in gas laws, which was chapter 9. Nope, 10. One of those, 9 or 10. And then when you increase that, the number of molecules will have enough energy to overcome that activation energy, and therefore reaction rate will also increase. So here we're going to see a lot of these graphs as we go through. They're really going to show up in chapter 19 and 18, really 18 more. This is called a Maxwell-Boltzmann distribution curve, and you may have seen one in chapter 9 or 10. And what it's saying is all of the same types of reaction have this one activation energy, but the higher the temperature, the more likely it is for more of the particles to collide. So more of them will have that activation energy, the energy required to make the reaction happen. So then you're going to have more products. Okay, once those collide, then you're going to have two factors. One is, do they have enough energy, the particles? The second one is, do they collide with proper orientation? So this first one is the enough energy they need to have that activation energy. Okay, otherwise they won't result in a product. And then they need to collide in a proper way, which I'm going to show you. So here, the reactant molecules have to have enough kinetic energy, so when they collide, they're able to have the reaction happen. If they're going too slow, it won't do that. And the more collisions per second, so the faster they're going, the more collisions that can be effective and lead to that product. So we're always going to be looking for those effective collisions. And that's that they've had enough energy to overcome the barrier, that activation energy, and that they have the proper orientation. Okay, and that proper orientation, that's when the atoms are aligned in such a way that the old bonds can break and new ones are going to form. So here in this picture, we've got NOCl, and they're forming NO and Cl2. And notice, the pieces that have to hit together are the ones that are going to stick. And you're never going to be asked to predict which pieces are going to need to hit together, but you are going to need to know that the activation energy and the orientation are what make an effective collision. Okay, if they do not hit in the right spot, they're not going to have that effective collision. All right, so now we're going to go on to mechanisms. Mechanisms are very important, and they're going to kind of be like Hess's law in chapter 9. So if you were good with Hess's law, that's great, because it's going to appear again in chapter 18. If not, I will review it then. Okay, but this is a series of reactions that we see the overall observed reaction, and this is called the mechanism, the series of them. Okay, so we've got this overall reaction at the top, and the point of this is that your series make the overall reaction. And the way to test this is to cross out what's the same on both sides of the arrow. Okay, so once you've done that, the rest of it should match your formula or your equation that you're looking for. The pieces in the series are called these elementary steps. Okay, here they're showing you HI's crossed out. Okay, and this is very important because you may be asked to identify intermediates. Those are things that are used in an early mechanism step, but then appear again as reactants later. So an intermediate start as product, and reappear as reactant. That is an intermediate. So they're not really affecting the overall reaction. They're appearing and then they're getting used up. Okay, molecularity. I'm not going to test this, but these are pretty simple. If we say that a reaction is unimolecular, that means there's only one particle. If it's bimolecular, that means it's two, but they could be two of the same particle. And then termolecular means there's three particles, and you could have bigger ones. Not normally, though. Okay, so when you encounter a mechanism, you do want to write the rate law from both, or from all the pieces. And it's always good to write the rate law from the one you're looking for. Don't forget your K. Remember, these are the products. Okay, and now the coefficients become exponents. They don't do that when you're doing it experimentally. But for now, they can. Okay, so you write the rate laws, and then generally you pick the one that matches it. In a rate law, you cannot have intermediates. Okay, and the rate determining step is always going to be the slowest step. Okay, this is kind of like in this picture down here, when there's traffic, you can only go as fast as the slowest traffic, especially when you're down to one lane. Okay, so that slowest step is the one that's going to have the largest activation energy because you can't go faster than it. So here we're looking at our proposed mechanism. Let's pretend they didn't tell us how fast they were. They just gave us the mechanisms. We wrote our rate laws. We looked at our rate law from above. Oh no, it tells us this is the observed one. Okay, so then at that point, we're looking for the one that matches. That gives us the slow step. Okay, also remember, intermediates cannot be in the rate law, and there's an intermediate there that's in the rate law, which means 2 is out. If you ever encounter an image or a graph with our activation energies, this top one, the one that's got the highest hump, that is the slow step. Okay, and this one happens to have 2 steps because there are 2 humps. If we saw 3 steps, there would be 3 humps. Okay, and when we're doing a mechanism, 2 conditions have to be met for it to be valid. The elementary steps must add to the overall reaction, and the rate law predicted by the rate determining step is consistent with the overall rate, even if it's just an observed rate. You may substitute a rate law of the rate determining step. Okay, and I'll show you how we do that in just a minute. Okay, so here it's showing us, I wish it let me go step by step instead of doing it this way. Okay, they told us the observed rate law. The problem is we've got this intermediate in our slow step, which means it's not valid. But every time you see this double arrow, that means it's in equilibrium. So when they're in equilibrium, remember the forward and the reverse reaction have the same rate. Okay, and we talked about that some in chapter 13. But I can replace NO for N2O2. When I do that, this reaction becomes this, or the rate law, and then that does match our overall rate law. Ooh. Okay, sorry, didn't mean to zoom in. All right, so this is our overall reaction. First thing we need to do is check that our overall reaction matches from our mechanism. So as you can see, O is an intermediate, and we're left with 2O3 yields 3O2. So we're good there. Again, the next thing you should do is write the rate laws. Rate is equal to K times O3 and O. And then rate is equal to K times O3. All right. So one problem we have, is that the rate laws don't match the observed rate law. Also, the slow step, which this is my rate determining, has an intermediate. But notice we've got this, so we can adjust for that. So because of that, the rate on one side is equal to O3, which is equal to the rate of O2 times O. Okay, remember, we're trying to get rid of O, so I need to solve this equation and just have O on one side. So I'm going to divide by K and then O2. I'm going to get rid of that, and my K's are going to cancel. Okay, so for O, I can replace that with O3 divided by O2. Since this can go in there and substitute, that means my rate is equal to K times O3 squared divided by O2, which is the same as this. So this is a valid mechanism. Okay, this one wants me to predict an overall reaction rate for the rate law. So again, we're going to cross out our intermediate. We're going to write our rate. Rate is equal to K. I guess we're assuming that's a something. Okay, so it seems to me like this would be our rate based on this mechanism because it has to come from this slow step. A catalyst is a little different than an intermediate, and then a catalyst starts at the beginning and gets canceled out later on. So it starts as a reactant, but then it's used up as a product in a later reaction. And as you can see here, Cl is a catalyst. Okay, and what they're doing is they're providing an alternative mechanism for the reaction with a lower activation energy. So yes, normally they do speed up a reaction, but it's because they lower that activation energy. Also, they're not consumed, they're just helping it along. Okay, and as you see in this graph, this would be the activation energy originally without a catalyst. And here is our activation energy with a catalyst, so much, much lower. Okay, just some basic definition. A homogeneous catalyst is when all the species are in the same phase. Then heterogeneous is when they're not in the same phase. And like I said, they do speed up a reaction, but they do it by lowering the activation energy. Some common examples of catalysts are going to be the catalytic converter. Pretty much all cars that I know of have them. And my first car had to have it replaced several times, which was kind of irritating. But it takes, generally there's a solid in there, and then we're putting gas through it. And so the solid is in a different phase than the other particles. Therefore, it's in a heterogeneous catalyst. Okay, and here's another image so you can see the particulates. The homogeneous, everything's in the same phase. In this example, they're all gas. And that heterogeneous, again, we've got that solid at the bottom, and then we've got gases at the top. And that is it for chapter 14. Okay, y'all have a good day.